Now we know what does it mean thermodynamic functions, thermodynamic systems, and let's talk about all thermodynamic function of state. First function, internal energy. Internal energy is a function of state which characterized total energy of physical and chemical system. Being the energy that's required to create this system, but excluding the energy which we need to displace this system environment, and which we need energy which we need to sit with to move this system, or energy as a result of external force. Internal energy is composed of contributions from kinetic and potential energy of all system, and value of internal energy can be altered by heat in the system or by work done on the system or by the system. But one note that we can't experimentally determine, we can't define absolute value of system in exact position, in exact state, in initial and final state. So in practice, we calculate just change of the internal energy. So we always calculate delta U, not just absolute value of this energy. Dependence and proportions between work, heat, and of course internal energy we can see in the first law of thermodynamics. First law of thermodynamics is a particular example of law of conservation of energy. And it tells us that energy can never be created nor destroyed, but just transformed from one state to another state. And heat that released or absorbed by our thermodynamic system, this heat goes to change internal energy of the system and goes to work performed by the system in our environment in given conditions. Well, now let's use this first law of thermodynamics in different thermodynamic processes in isochoric, isobaric, and isothermal conditions. Firstly, let's see how it works in isochoric conditions, so when we have constant volume. So you see here in the formula I write QV, and of course we write delta U, change of internal energy, and sum it with work of this system. But this work we can write like pressure, like product between pressure in our system and change of volume. But they said that we use this first law of thermodynamics in isochoric conditions, so we don't have exchange of volume, change of volume, and this system doesn't produce new work. So work equals 0, and in our situation QV equal delta U. It goes just to change of internal energy. Sometimes in the final test, in final exam, I can ask you, to which thermodynamic function of state equal heat that released or absorbed by the system? And in isochoric condition, we can say that this thermodynamic function of state is internal energy. Next situation. Now we have constant pressure. The same, we write QP right now, and this heat released or absorbed by the system goes as well on change of internal energy and goes to work. But now we have constant pressure, so work has a special amount. And this last term in this equation, P delta D, is the energy required by the system to change volume. against the constant pressure of the atmosphere. And this energy we call it like pressure-volume work. Thus, the equation says that the internal energy of the system changes in two ways. Of course, it goes to heat or to cool our system, and you see here change of internal energy like just pure heat, and exactly in this picture, in reaction between sodium and water, heat of reaction minus 368.6 kilojoules, but as you see in this picture, we have change of volume because this reaction between metal and water produce hydrogen. So we make work. This work goes to change of volume and increase volume against the constant pressure, and it requires energy P delta T. Exactly in this situation, in this reaction, this pressure volume work equal minus 2.5 kilojoules. And you can see that actually difference between delta U and one more thermodynamic function, delta H enthalpy, is not great. But in a constant pressure, you can see change of heat effect of reaction, heat that is released or absorbed by this system equal to change of enthalpy. You see that first in this equation we placed in two frames change of internal energy and change of work in two different states, second and first one. But then we placed in two frames exactly final state, U2 plus P V2, and minus initial state, U2 plus P V1. And we can rewrite these frames through second thermodynamic state function, enthalpy, H2 minus H1, and finally we have change of enthalpy. As well as internal energy, unfortunately, we can't experimentally determine absolute value of enthalpy for exact system in initial and final state, so we just can calculate difference of enthalpy in different processes. And they said that we have isothermal processes, so these reactions, with this process goes, then temperature is constant, and in this situation all heat goes just to the gas expansion. So for 1 mole of ideal gas, what we have? Qt, so heat effect of this reaction, equal just work, so equal to the product between pressure and change of volume. But we remember that we can calculate pressure of this gas, partial pressure, like ratio between gas constant and temperature or volume of this gas. Thus, we have the next calculation. Heat effect or heat in our system, Qt, equal to gas constant multiplied by temperature and neutral logarithm from ratio between volume in last position in second state and volume of initial state. If in different calculation in exact task we have instead of volume we have pressure, exact pressure, we also can put it in these calculations, but now we can recombine these calculations and we write RT multiplied on neutral logarithm, but now ratio between pressure in initial state P1 and pressure in final state. Before we start calculations for exact chemical reaction, we also need to know that we have two different types of reaction from position of quantity of this reaction. You already heard that I said several times heat effect, thermal effect, but what exactly heat effect of reaction, not of system, but of chemical reaction? It's a heat that absorbed or released by system as a result of chemical reaction. For example, if we have combustion reaction, you feel heat, so we can say that this is heat effect or thermal effect of combustion reaction. And here we have two different types, endothermic reaction and exothermic reaction. You can see it in this table and in these two pictures. So first, what does mean endothermic reaction? Then system need energy to start this reaction, because all substances consist of molecules. Molecules in turn consist of atoms, and between them we have bond. And to start this reaction, we need to put energy to break bonds. So in this situation, you see endothermic reaction. We add any portion of energy, so heat goes to this system, into this system, and sign of heat is positive plus, and we can say that change of enthalpy or change of internal energy higher than zero. And of course, what we exactly calculate change of enthalpy or change of entropy depends on conditions, isobaric or isochoric conditions. And then the system lose energy, for example, as I already said, combustion reaction, or maybe neutralization reaction, or maybe you want to make a solution of any hydroxide of sodium hydroxide, and then you put sodium hydroxide exactly in the water, you feel then glass in this case become warmer. So in this situation we have exothermic reaction, so energy released, and in comparison with the initial position, system lose energy, so sign of this heat effect of this heat is negative, so delta H and delta U lower than zero, and you can see it in this in these pictures. Okay, what about exact substances and calculation for reaction? All functions of state functions depend, as we already said, on the mass of substance, and generally it referred to just for 1 mole of substance. So now we need to, in this situation, we need to use 2 parameters in which we call like standard heat of formation and standard heat of combustion. I wrote here in the frames standard enthalpy of formation, because mostly we make experiments in isobaric condition, actually isobaric isothermal condition. For example, if we want to make any experiment right now in our room, we have atmospheric pressure, and we can say that it's constant pressure, so we can say that we need to use here standard enthalpy of formation. What does it mean? Standard enthalpy or standard heat of formation is a heat which we need to give for this system to form just 1 mole of complicated substance from simple substances in standard conditions. So I mean, then temperature is a room temperature, 298 kelvins, and pressure, atmospheric pressure is 1 atmosphere. Standard heat of formation for complicated substances were experimentally determined, and it's given in thermodynamic data in special tables. So if in your final set you have a task to calculate heat effect of any reaction, standard heat of formation will be given for you. And you see how we can express it. We write delta F H, and we express through index 0 and 298 standard conditions, and units for this parameter kilojoules per 1 mole, because I said that standard heat of formation is a heat that we need to produce just 1 mole of substance. And as well, we need to keep in mind that we produce it from simple substances. But simple substances can be in different allotropic forms. For example, for carbon, we have graphene, we have graphite, diamond, and what we exactly mean here, which allotropic form we use to write reaction for standard heat of formation. For standard conditions, we use such form, which the most energetically favorable for this substance. And I said that we unfortunately can determine absolute value of enthalpy and internal energy. So we need like a reference point. And reference point for standard enthalpy of formation is a standard heat of formation for simple substances. And in thermodynamic table data, you can see that for the substances, standard heat of formation equals 0 kilojoules. But I said that most reactions in our world are combustion reactions. So for this reaction, we use, of course, standard heat of combustion, and you see difference in expression. Now we write delta C, H0 298 kilojoules per mole, and this heat that our reaction produce in combustion reaction of 1 mole of organic substance, because usually we use we have combustion reaction with organic substances, and these substances burn in pure oxygen, because we as well can make combustion reaction in atmosphere, but our air or atmosphere, it's a mixture of different gases, nitrogen, oxygen, hydrogen, and so on. But for standard heat of combustion, we can say that we burn complicated substance, 1 mole of this substance, in pure oxygen, and this reaction produces highest oxide. What does it mean, highest oxide? When element of oxide in this substance, the highest one. For example, for carbon, we have monooxide and dioxide, CO and CO2. And we can say that CO2 is the highest oxide because carbon here in its highest valency equal 4. Exercise number 1. We need to write thermochemical equation for this substance. NH4 doubled, platinum, fluorine 4, and 2 hydroxide group. How we can write this thermochemical equation? First of all, we need to know that in thermochemical equation we write heat effect of this reaction exactly for pure complicated substance. It means standard heat of formation. Standard heat of formation is a heat that we need for formation reaction to produce just 1 mole of this substance. And we remember that we produce this substance from simple substances. So we just need to see which simple substance we have in this complicated. We have nitrogen, we have hydrogen, platinum, fluorine, and oxygen. And we need to produce 1 mole of this substance plus delta FH0. Now we need just balance this equation. So according to complicated substance, we have just 1 mole of nitrogen and 5 moles of hydrogen, 1 mole of platinum, 2 moles of chlorine, and just 1 mole of oxygen. So now we have thermochemical equation for formation of this complicated substance.